You were thinking of that assignment too? No, well, if you're done with it, I have good news because there is an extra credit assignment 2 for those who want the extra challenge. But I was thinking about lab assignment 1. If you're not done with it, you have extra days, 5 days as you know, 5 total over the semester. So use them wisely. Okay. My PowerPoint is not behaving well today. That's better. Okay, we're going to cover multi-cycle microarchitecture today, but as I always do, reminders for you. Homework 1 solutions are posted. And please check and study the solutions. It's better to do it right now than rushing later, before the exam. Homework 2, you know that it's due sometime next week, right? February 13th. Lab assignment 2, lab assignment 1.5 will prepare for you for it. And 2 is due on February 17th, and this is an individual assignment. Please respect it. Even if there is no honor code, we're all honorable human beings, so make sure that you do it individually, and you will learn a lot better if you do it individually. There is an extra credit also. We realize that some of you turned in lab 1 early, and some of you seem to want the extra challenge. So if you are done early with the single cycle implementation that we asked for in lab assignment 2, you can go ahead and do a microcoded implementation, as we will talk in class today. Well, partly today and partly next week. And we're going to give you flexibility in this so that you can exercise your creativity if you want. We're not going to specify anything with regard to the microcode implementation. You will see that the microcode implementation has multiple parts: the control store, the microsequencer, and the data path. And we're not going to specify any of that. It's going to be up to you, so you can be creative. And it'll be your burden to show to the TAs that actually it works. Because it's an extra credit assignment, so the bar will be high. And your microcode implementation should execute the same programs your ordinary single-cycle implementation does. So this is by no means required, by the way. Don't be intimidated if you're seeing this. Oh, we're going to do a microcode implementation on top of a single-cycle implementation in 2 weeks. Well, if you're done with the single-cycle implementation, if you're excited, feel free to do it. If not, you will not be penalized for not doing it. This is purely for extra credit for those of you who want the extra challenge. Is that clear? Okay. Some feedback on lab assignment 1. Well, my TAs are working hard on grading your assignments. And we will have comprehensive tests for all of the labs, so make sure you test your labs very, very well so that you can pass our tests. Actually, if your tests are more comprehensive than ours, that's good, right? Lab 1 tests exercise every case of each instruction as well as long programs, for example, repeat MOVEs. And we will release a test case and register dumps after we're done so that you can fix your implementation if you wish, so that you can use it for later on, because you're going to use this reference simulator for your later labs. So some advice based on what we've seen so far: be thorough and test all possible cases. Make sure your code compiles. That's the first step, I guess. Follow directions. They're there for a reason. We've seen multiple cases where people have modified the shell code. Even if you modify it for your own purposes, please don't turn it in. No modifications to shell code. This is important for us because this eases grading a lot. We auto-grade quite a bit of your labs. And if you modify the shell code, that gets in the way. No unaligned accesses to memory. That also gets in the way of grading. We did not specify this, but we will specify this for the later labs. When you turn in your code, remove all debugging printfs. That gets in the way as well. You guys all know C, right? you can do pound ifdef, and you can have a debug compile statement, and printf can be enabled only that debug option is enabled to the preprocessor of the C. That could be one way of doing this. That way you don't need to remove all of the printf one by one. Well, if the lab is too easy, do the extra credit also. That's another feedback. Okay, readings for today. Hopefully you've done these because we will cover heavily Pat and Patel revised Appendix C. And for understanding Appendix C, you will need to know Appendix A. You don't need to know how exactly each instruction operates, but you can refer to Appendix A, right? And Appendix D in Patterson and Hennessy covers some of similar concepts in a different way. And the optional reading for the enthusiast, if you will. How many people read this paper? No one yet? Hopefully in the next lecture when I ask this question, there will be at least one. This is the reading for next lecture. I'm not sure if we will get to it, depending on how we progress in this lecture. But we will definitely get to it next week. So we will cover pipelining next week, at least basics. So let's review the last lecture to warm up your caches. You guys know the instruction processing cycle, right? The instruction processing cycle, we covered 6 steps. So if I ask you this question, what phases of this instruction processing cycle does the MIPS jump and link instruction exercise? Will you be able to tell me? I won't be able to tell you without looking at my cheat sheet, the green sheet. Anybody? I guess I'll give you a hint by showing you the instruction processing cycle. This is it, right? You fetch an instruction, decode an instruction, evaluate address, fetch operands, execute, and store result. Every instruction goes through these, but not all instructions actually exercise each of these steps. This is the generic cycle. Well, regardless of what instructions is, you'd better fetch it and decode it, right? Before you do something with it. So all instructions go through these 2 steps. The question is, does the jump and link instruction, which does this? So if you look at this cheat sheet, and hopefully it's correct, it specifies jump and link as this. It sets R31 to program counter plus 8. 8 because there's a delay slot in MIPS, which we will get to. And it sets the program counter to jump address, where jump address, well, let me actually do this. So you better set the jump address first before setting the program counter to it. What is it? It's essentially PC plus floor, top 4 bits, concatenated with, ooh, there's an address here that comes from the instruction, right? Oh, yes, it comes from the instruction with the bottom bits, bottom 2 bits, 0. So basically, this address comes from instructions, I guess, bottom 26 bits, right? Yeah, I'll call this the instruction register, bottom 26 bits. Shifted by 2, concatenated with top 4 bits of PC plus 4. So what phases do you exercise in this case? Well, anybody? You definitely do execute. How do you do execute? Well, I guess it really depends on how you define the phases, right? I would say you evaluate address because you're really evaluating an address here, the jump address, by doing this computation that I told you. I guess, are you fetching operands? You're not really fetching operands, right? Because the operand PC is already available to you. Yes?
Isn't the can't jump and link take a register other than register 34 or register link?
No. According to this specification, it cannot, right?
The full-blown manual said.
Oh, it can? Or JLR? JAL?
Whatever is in RD. So by default, the pilot has to turn on.
That could be JLR. Jump and link register. Yeah. Maybe I should have done that then. Then that would have exercised the fetch operands, right? That would have fetched the... Well, no. That would change the destination, right? That wouldn't fetch the operand. So you're not... Yes?
That would also be the source, because you take two registers or alternatively one register.
I see. Okay. Okay, that would change the source. Then you would fetch the operand. Yes?
Does fetch operand only mean fetch from memory?
That's right. Yes. Or fetch from a register. Here you're not fetching from memory or a register. Actually, you're fetching from a special register, but that's already available. You're not really... You're implicitly doing that. So you're really evaluating an address here, and at the same time, you're storing the result into a register. Right? Are you executing? I guess if you consider this part as execution, then you are executing. Make sense? Okay. Okay, let's go back. I guess it's an easy question. How many cycles does it take to process an instruction in the single cycle microarchitecture? 1, right? That's why it's single cycle microarchitecture. What determines the clock cycle time? You have the combination of logic to process the slowest instruction, right? And we will see this very clearly today by studying the design that we looked at last time. Well, we first complete the design. What is the difference between data path and control logic? Hopefully you know that. What does data path do? Yes?
Data path is different elements. Control logic is where you can take a particular path.
Okay, that's a good start. So data path essentially are all the elements that actually operate on data signals, right? Transform data signals. And control logic determines how those elements actually do that transformation. So, well, this is a slide from before. That's why it's called review. So you should know these very well. We also covered combinational versus sequential control, right? You could implement the control logic as combinational or hardwired, or as a control store that stores all of the control signals, and you pick the right control signals based on the instruction you're processing. So that's another thing that will become clear today. Actually, if you read Appendix D in Patterson and Hennessy, which was your required reading for today, you will see the difference. But in the single cycle microarchitecture we'll look at combinational control. But we will cover sequential control extensively with the microprogram implementation. So what is the semantics of a delayed branch? We had a little discussion about this. That made some of you upset because you didn't quite understand exactly why this was there. And I don't blame you because we haven't really covered it. But you have studied the MIPS ISA. What is the semantics? Yes?
The instruction after branch is always executed.
Exactly, yeah. So the instruction after the branch, let's say you have a branch here, you have another instruction here at, let's say this at PC, you have another instruction at PC plus 4. The instruction after the branch is always executed, which means that the branch really takes effect after this instruction is executed. Make sense? If you're jumping to a target or not jumping to a target, regardless of that, this instruction is always executed. Yes?
So if you actually did not want anything to happen after the branch, you'd have to put in like a no-op?
Exactly, that's right. If you cannot find an instruction to place here to the delay slot, this is called the delay slot, and the branch takes effect in a delayed manner after the next instruction is executed, then you just put a no-op here. That way, there's no harm done, if you will. Right? Now, lots of questions with delayed branch. I don't know if I want to handle all of them, but you can.
Since we're not doing delay slots, are we also not going to do the branch with likely bit set in our implementation?
Branch with likely bit set. That's a good question for Chris. No, Chris says
Maybe in the lab when we do branch prediction. That'll come later.
yes. So don't worry about that right now, but when we come to the branch prediction lab. But you don't need to worry about it now, because why people have made this design choice will become clear later on. Yes.
It also seems to have some other funky behavior with respect to unconditionally executing things that you think are conditional, like the thing instructions that do a comparison and then jump in length unconditionally via the length and then have to go to branch.
Okay. Joe? Yeah, I mean, there are such ISA design choices that were made. And there are reasons for it, but I don't want to go into those right now. And you will see the reason for this one. Okay? Any other burning question? Yes? Since you answered the previous question, you get a chance to ask a question too.
Okay, so instead of putting a no-op, which is just like a waste, but just lots of times you just take the one before the branch and like does it help just move it onto the branch? It is independent of the branch.
Yeah, exactly. If you have an instruction here that's independent of the branch, you can move it here. Right?
So does the compiler automatically do that?
Yes, the compilers do that, and that's how they fill the delay slot. But what if there is no instruction here that's independent of the branch? Then it's very tough for the compiler to figure out what to put here. Then there's a no-op that's put here. Okay? And this will become very clear when we cover pipelining. I just want to warm you up with the semantics. All you need to know right now is the semantics of it. Okay? Okay. This is to answer the questions. So today, I'd like to finish the single cycle microarchitecture, and we'll look at the critical path of the single cycle microarchitecture. We'll cover some design principles, which are probably violated by the single cycle microarchitecture. Talk about some performance evaluation very briefly, and then jump into multi-cycle microarchitectures and microprogram control. And hopefully, you all have handouts that are figures from Appendix C of the pattern Patel book. And that is needed for multi-cycle microarchitecture. Okay, just a few more advice so that you can make the best out of 447. I really recommend you to do the readings. Actually, some readings are required. You should really do the readings. And you will understand the lectures a lot more if you read this lecture, for example, a lot more if you read Pattern Patel appendices A and C, especially C. Well, you may not be able to read Wilkes' 1951 paper, but it's good to read the fundamental papers that have introduced things. And it's not a required reading, it's optional reading. Do the assignments early, don't delay them, because there will be more assignments coming. And I don't know if you're aware of this, I didn't really formally announce it in class, but we always put up buzzwords at the end of every lecture. How many people were aware of this? Not everyone. Okay, half of you, or less than half of you. So this is good to study. Actually, let me spend some time and show you the website. There's a reason why my TAs are here. They're also taking notes, because I cover a lot of things that are not necessarily on the lecture notes, right? And if you go to lecture schedule on the web page, you will see that actually we've already posted some videos as well for those lectures where we have the videos. If you want to go back, you can watch the videos. If you're not already bored of me lecturing for 2 hours in each class. But if you look at the rightmost column here, you can see the buzzwords from lecture 1. And hopefully this will give you a good idea of what we have covered in the lecture. Things that are not necessarily on the slides. Is that good? So I would recommend you to study these buzzwords after lectures so that you can see if you actually capture the things. And feel free to ask questions during office hours to the TAs as well as me on any of the buzzwords. And I recommend taking notes during class. Okay. Okay, this is what this full single cycle data path was. You'll remember this, right? Can you see this from the back? Okay. This part is not clear to me from here. And we were constructing this, building up to this. I showed you this initially. And what we did was we looked at the single cycle data path for arithmetic and logical instructions, and we designed it. And this was the data path for R and I type ALU instructions. Complete data path. Basically, if you have an I type instruction, you would choose one of these destination registers. And I type chooses which one? 20 bits 20 through 16 in the instruction as the identifier of the destination register, right? Because the other operand is an immediate, while the bottom bits are really coming from the immediate. So you should be very familiar with the data path for ALU instructions. And then we covered the ALU, the data path for data movement instructions. And this is the complete data path for non-control flow instructions, including ALU, as well as load and store. So just to warm you up, I guess I can show you what happens to a load. Basically, you fetch the load first, and you, I guess what happens when you do a load? You need to read the register, right, that you're loading. Well, you need to first compute the address, I guess, first of all. So there is a register through which you compute the address. And read register 1 specifies the base register. And you have a displacement in the load instruction that's sign extended and selected by this mux. And address is computed that way. This address is fed into the memory, and data is read out of memory. So if you have a load memory read signal is asserted, and the source signal specifies this sign extended immediate from the instruction, and address is fed into memory. You get the data back from memory. This mem to read signal specifies that it's a load, which means that data actually comes from memory, right, instead of the result of the ALU. And this data value is input to the write port of the register file, and register write is enabled if it's a load instruction. And so this is the data path, and you set the control signals accordingly when the instruction is decoded. And we don't show the control logic here. Okay? We were at the control flow instructions, and we covered how to do the data path for the unconditional jump instruction. Again, just to remind you, this is the machine encoding. You need to know the machine encoding to design the data path as well as the control, right? This is the machine encoding. You have a 6-bit output that specifies a jump, and you have a 26-bit immediate. And we already looked at how the jump address is computed. The difference between jump and JAL, jump and link, is jump and link also saves the next program counter in R31. Here we don't save the next program counter. So if the instruction is a jump instruction, the target address is computed and PC is set to it. So what do you need to do for that? Basically, you need to have logic in the data path to compute the target address as specified, which is this logic. You take the instruction bits, concatenate them with the program counters, top 4 bits. Well, you need to shift the instruction bits, or you get rid of some of the instruction bits, right? And then you need to have a mux going into the PC that chooses either PC plus 4 or the jump address. Well, if it's a jump instruction, this is jump control signal of the mux is asserted, which means that the program counter value comes from this concatenation logic instead of PC plus 4 adder. Make sense? Well, in this case, in your lab, you're really not implementing delay slot, so I already removed the delay slot here. And we already also discussed how to do jump and link, right? Well, I guess this is jump register. This is not jump and link. What does jump register do? Jump register doesn't compute the address this way, but if you look at this, it essentially computes the address this way. This is jump register instruction. It does this. PC equals register RS, which means that the PC needs to be fed with a data value coming from the register file, and that path doesn't exist in our data path so far. So to be able to implement jump register, you need to take the data value coming out of the register file and feed it into the PC mux, if you will, and enable the control signal. You need to change the control signal. Now you need 2 bits in this mux, right? And the mux is wider. Okay? And if you want to do a jump and link, there is an extra path that I will let you figure out. Jump and link does this. We looked at this. To do jump and link, basically, the jump address is the same as what we did for a regular unconditional jump, J, if you will. So you set the control signal such that the program counter is set to this mux selects the signal coming out of this concatenation logic. But you also need to do something else in the same cycle, which is this, right? And basically you take, I guess, program. I guess this is not true, is it? You really need to take PC plus 4 here. So I have a bug in my data path. We should correct this before we post the slides. So if we eliminate the delay slot, this should be PC plus 4. So you take the address of the next instruction, program counter plus 4, and connect it to the write data. Now, that means that write data can come from 2 places, right? Write data, port, the data that's to be written into the register file can come from 2 places. Not only from memory, well, there's another mux here, but not only from this mux here, that you should imagine, because I showed you before, but also you could write into the register file from the PC plus 4 value, which means that you need another mux here. Right? So if the instruction is a jump and link, or JALR, that needs to be enabled. Okay? So you will need to design this in your single cycle design. And actually, that single cycle data path is given to you. You will need to design the control. Okay, so how do we do conditional branch instructions? This is something we did not cover. A conditional branch is encoded this way. It's an I-type instruction. It has an R source, and it's an RT, and an immediate. And target is determined this way. PC plus 4 plus sign extended immediate shifted left by 2, right? Or multiplied by 4. And if the registers, this is the BEQ, one particular type of the branch instruction, if the source register is equal to the destination register, that program counter is changed to the target. You jump to the target. Otherwise, you go to the next sequential instruction, which means that you need to provide all the support. And I think this is with the delay slot, right, Chris? That's all I have. So this is, you got to be careful in your implementation. And we specify this very clearly in your lab such that the delay slot is eliminated. So you should, I think this should be PC plus sign extended, or no?
I think it's still PC plus 4.
Oh, it's still PC plus 4?
Yeah.
Okay, good. Okay, good. I thought I made a mistake, but that's fine. So this is consistent with your lab specification. But read the lab specification very carefully because we carefully specified those instructions. And Chris sent out an email related to this. That's why there's a watch out here. Look at the specification. So what do we need to do to implement this? Basically, we need a way to compute this target, right? So how do we compute this target? Well, let's see. I guess then my data path is incorrect. Is that true? Let's see. So first of all, you need to be able to source the RS and RT. Now RT acts as a source, right? So you source RS and RT, and ALU specifies a compare, if you will, subtraction, right? And you need data path. You need if the 2 registers are equal, then when you subtract one from the other, the result will be 0, right? And if the result is 0, you need to have data path logic to check that. Then your condition is satisfied, which means that your program counter should be calculated as this target, PC plus sign extended immediate times 4. Right? let's see if this is true. I guess PC plus sign extend immediate shifted by 2. Except that should be PC plus 4, right?
Yes.
Yes. So really this should be coming from here. You need to be able to do the concatenation here. We will see this in the full data path. There you go. There you go. This is the real correct one, if you will. Ignore this for now. How does the branch operate? You have PC plus 4, shifted left by 2, and that's how you get is that true?
Isn't that the jump address?
Yeah, that's the jump address, right? So this is the 16-bit immediate. I don't know if this data path includes that. Let's see. I have to find it now. Yeah, there's a sign extension here.
Upright.
Oh, there you go. There you go. Yes. There you go. This is the data path. So why did? Oh, there you go. Okay. It's also here. So I did not have the animation correct. Okay. So let's look at this. So what? You have the program counter. You get PC plus 4 here from here, right? This is the adder that computes PC plus 4, and you need to add to it the sign extended bits from the instruction, right? 16 bits, bottom 16 bits from the instruction, which is this logic already exists here, right? And we need to shift it left by 2, and we add another adder into the data path. Why do we need another adder? Because this adder is doing the comparison for the branch, right? So this adder determines the branch condition. This adder determines the target by taking PC plus 4 and left shifted, sign extended, bottom 16 bits of the instruction, and you get the branch target. Now, what you need to do is to extend this much again with another input, because this input did not exist when we implemented unconditional jump and other jump variants, if you will. Now this branch control logic is becoming more complicated, right? It's not a single bit. Now this output of the ALU is input to this control logic here that determines what should this mux pass to determine the program counter in the next cycle. Right? And you are responsible for implementing what this will be. I will not tell you, of course, but based on the opcode, you can easily figure out whether you take this branch control logic. Okay? And don't worry about the delayed branch semantics. That will complicate this design. Just think about what will happen if you had a delayed branch. Right? If the next instruction was always executed. What do you need to do then? You cannot just take the target right away. You need to wait one more cycle. Okay?
Another input that wants like reactive and then
That's right.
cycle
Yeah.
add
Basically, you need to latch this.
Right.
Or you need to latch anything that comes into the program counter except PC plus 4. So whenever you have a branch instruction, the target needs to be latched. Right? And then that needs to be fed into the program counter not in the next cycle, but at the end of the next cycle. Okay? But you don't need to worry about that. It's already confusing as it is. Make sense? Is it clear now? Okay. Now this is the full data path that puts it all together with all the instructions, and we've omitted some of these, but you can see the full data path in the book. And I guess let's take a look at the control logic that controls this data path. I've given you some bits and pieces of it, but we haven't really designed it, if you will, and I'm not going to design it for you because that's really your lab, but I'll give you how we could go about designing it. So this is the control logic, right? Control logic takes the instruction opcode and determines what your control signals are. And there's also other control logic, for example, the ALU control logic, that takes some bits from this control and also some other instruction bits, like the bottom 6 bits, for R-type instructions, right? Remember, the R-type instructions have opcode 0 that specify that these are ALU operations, but what your function is really specified by the bottom 6 bits in the instruction. So that is essentially control logic. And also, control logic is everything that controls the behavior of these data path elements, like the muxes. So you have a bunch of control signals that control that behavior. How do you set those bits? How do you set the and in each cycle you need to set the bits correctly so that the instruction is processed according to the specification. So here's one way of doing that. You could do this in a hardwired manner, basically as a combinational function of the instruction at this memory location. Right? You take the bits in the instruction and basically check them, and based on that generate the control signals. So let's consider some of these instructions. Ooh. I guess my PowerPoint blew up here. But there are a bunch of control signals. For example, you start with the data path that's given to you. You're not designing the data path for this lab, so assume that it's given to you. For example, there's a control signal that says register write, or I guess register dest is a different control signal, right? Register dest is a different control signal, which basically specifies what is the destination register. And you know that if the instruction is R-type, the destination register is RD, otherwise it's RT. Okay. So you can simply check if the opcode is 0, that's the only case when the destination register is RD. Right? So if the opcode is 0, then regdest should be deasserted, if you will. Well, it depends on how you specify the control signals. It's deasserted here, right? Basically, if the instructions are type, you pick bits 20 through 16 from the instruction as the destination register ID identifier. Otherwise, you pick bits 15 through 11 as destination register identifier. So you can design the control logic for that particular mux signal very simply by checking the opcode. Similarly, you can do the same exercise for all of these control signals. I will not do it for all of them. And this should be fixed. This is the problem with PowerPoint Mac. There's no compatibility between different versions, and sometimes things blow up. But you will go through all of these. And these are actually specified in the book you should have read by now, the single cycle microarchitecture. I think sections 4.1 through 4.4 of Patterson and Hennessy. Right? And this is this table directly out of it, actually, although I've made things a little bit simpler for you here. So ALU source, for example. Well, should we take a look at that? I guess let's take a look at that in this data path. Now I have to figure out the ALU source. Okay. This is the control for this mux. Do you pick this input from the register file, or do you pick this input from the immediate, sign extend immediate, into the ALU? Well, I guess if you go through the instructions, figure out which one is immediate, right? If the instruction is I-type, then you really want to pick the sign extend immediate for that to operate correctly. Otherwise, you pick the source, from the, you pick RT, which means that the data from the register file. Let me go back. Make sense? But there is a little bit difficult here because branches also use this, right? Remember? What do branches do? So if the opcode is not equal to 0, you definitely know that, you would like to pick this one. If the opcode is equal to 0, let's see. If the opcode is equal to 0, you would like to pick the value coming out of the register file. but we're saying when the signal is asserted here. If the opcode is not equal to 0, then you pick the immediate. And, however, branches also don't have opcodes not equal to 0, right? But you don't want to pick the sign extend immediate to go into the ALU for a branch, because as we just covered, well, it's not on the board, but as we just covered, the branch compares two register values in some way specified by the instruction. So for those branch instructions, you want to ensure that the control signal of the MUX selects the input coming out of the register file. So if the opcode is also not equal to BEQ and not equal to BNE, then you pick the immediate. Then this MUX should pick the immediate. So you can design this control. This is the control logic that asserts the control signal for this MUX. Make sense? So that's what you need to do. For each control signal, figure out when should it be asserted, when should it be deasserted. And you know that you can design this based on combinational logic that looks at the output, as well as some other bits, as we will see for the ALU controls. Make sense? And there are some control signals that are hiding here that I would just like to show you here. That's the register write signal. If you look at the register write signal, you want to enable the register file to be written if this condition is true. Again, you can figure out that based on the opcode, which opcodes are actually writing to the register file, right? Okay. And there are other control signals, as you can see, and I'll let you figure out when do you enable the memory to be read, when do you enable the memory to be written, when do you get the targets of the program counter from different inputs that are controlled by two MUXes, as we have seen here. Basically, how do you enable these two? So designing the control logic hopefully will be fun. Okay. Also, you need to design the ALU control. Basically, this is a little bit more sophisticated because a lot of instructions actually use the ALU. For example, branches use the ALU, as we've seen. You will need to consider this ALU op signal. This says whether or not you'll actually use the ALU, and this will also determine how you will use the ALU if this is an R-type instruction. And your job is to take those inputs somehow and design the ALU control. And this is explained in detail actually in Patterson and Hennessy. So nothing you will do will be really magic. So if you find this too easy to do, then you will go to the microprogram control. Does this all make sense? Any questions so far? So basically you can have a case statement that looks at opcode. If the opcode is 0, it's an R-type instruction. And remember, R-type instructions specify what you need to do, what operation the ALU needs to do based on these bottom 6 bits of the instruction. If the opcode is an ALU operation with an immediate, then the opcode specifies what the ALU should do. So you should have some combinational control that generates what the function of the ALU should be based on that opcode. If the opcode is load word, then the ALU is used to compute the address. Remember? Register plus an offset. Then the ALU should do addition, right? Because register plus offset, that's the plus. Similarly, store word, ALU should do addition. Branch with some condition, then you need to select what ALU should do based on the condition specified in the opcode. Right? It could be branch equal, branch not equal. ALU should do different things based on that. And if the opcode is something else, which means that ALU is not used, then you can set the control signal to don't care, right? You can set it to anything. It doesn't matter because you're not going to use the output anyway. You're not going to use the output to write anywhere. Okay? No questions? It's all easy. So let's take a look at how this data path operates with some control signals. So if you have an R-type ALU instruction, yes, you can really look at things as what connections you enable in this data path, right? So this is how an R-type ALU instruction operates, right? You take the bottom, well, bits 15 through 11, and this MUX control connects those to the destination register ID. You enable register file to be written, and you add two registers coming out of the register file. So this MUX selects the register input. Memory is not accessed, which means that ALU result is passed to the right port of the register file, which means that this MUX control signal should be set to 0. Right? At the same time, you need to increment the program counter. Right? So these MUXes are set, the control signals are set such that PC plus 4 flows into the program counter. Right? So you could do this for I-type ALU also. The difference is now immediate, the destination register is specified by these bits of the instruction. You still write to the register file. This MUX selects the immediate input into the ALU. Memory is not enabled, so these are set to 0. Well, I forgot that opcode. Of course, this logic specifies what ALU should do. And you take, this MUX selects the output of the ALU and passes it into the destination port, right port of the register file. And again, these MUXes are, the control signals are set such that the PC plus 4 flows into program counter. Load word, you can go through it similarly. I guess I will go through it also. In this case, you have a destination register that's specified by RT. So this MUX selects RT. This sign extended immediate is used, input into the ALU so that you can do address computation. You have a destination register, so this is enabled. Register writes signal is enabled. This ALU function is set to add. And you do a memory read. So memory read signal is enabled. And read data is selected by this MUX, which flows into the port of the register file so that you can write the data that's read from memory into the destination register. So you can go through this data path and figure out the control signals this way for each instruction. Right? That's how you design the control. Okay, and again, program counter plus 4. Store word is very similar, except for several things. Right? You don't have a destination register, so register write is 0, which means that this control signal really doesn't matter, right? You don't care what destination register ID you choose. So this is supposed to be I don't care. But you still need to do the address computation the same way as a load. You don't read the memory, you write into the memory. And again, this path doesn't matter because you're not writing into the register file, so this MUX control signal can be don't care. And the PC is again incremented. If a branch is not taken, then this is the path that is taken, right? In the data path. The branch obviously doesn't write into the register file, so you don't enable the register file to be written. This is how branch computes its condition, right? There's a branch condition signal coming out of the ALU, and that's computed by looking at by doing an operation on two operands that is determined by the type of the branch, right? That is determined by this control logic that looks at the opcode. And the branch condition is generated, and if the instruction is a branch, and the branch condition is true, well, this is a not taken branch, which means that branch condition is false here. So this MUX control is set to 0. That means PC plus 4 flows into the program counter. Right? If the branch is taken, then the same thing happens, except this signal will be set to 1. Right? Now, the branch condition, the target address of the branch actually flows into the program counter. Make sense? Simple, right? Any questions? Jump is, again, if you see jump here, this is an unconditional jump, very simple unconditional jump. A lot of things don't care. As long as you don't write to the register file and you don't write to memory, you can set all of those mux signals to don't care because you're not doing anything there. You just need to ensure that program control is updated with the jump address. So this mux control signal is set to 1. Okay, what is in the control box? Well, that's what you will design. And there are 2 ways of designing it. It could be hardwired control. The idea here is control signals are generated combinationally based on the instruction, right? That's what I showed you. It could be sequential logic. And we will see this clearly, but even in the single cycle design, you could implement it as you take the opcode and perhaps some other necessary bits from the instruction. Only one of these. So you could have something called a control store. You can take the opcode and perhaps the function that's part of the opcode index into a memory structure that contains the control signal, that contains all of those control signals that we looked at, and opcode and the function together specify an address into this control store that's indexed. This memory is accessed, and the memory outputs the control signals. This is another way of designing the control logic. And you get these control signals, and they're fed to all of those muxes. Of course, you may need some other signals. For example, the branch condition cannot come from here, right? Because branch condition is really a function of something else than just opcode and function. You really need to read the register file and look at the data to figure out whether the branch is taken or not taken. So you take the control signals, some of the control signals, and process them with whatever needs to come from the data path to control the muxes. Yes?
Wouldn't you need more than one cycle to read into memory?
Well, we will get to it. We're assuming magic memory in this case, right? Yes?
But if it were just the same cycle, then it would just be combinatorial. If you could read in the same cycle, then would that mean it's combinatorial?
Well, yeah, you could treat this as combinatorial, right? We're treating the register file as combinatorial also. It's the same thing. We could read from the register file in the same cycle. So it's the same thing. You're just reading the control signals instead of the data. Okay? So there are 2 approaches to designing control, and these are the 2 approaches. Okay. So let's take a look at the single cycle microarchitecture. Let's evaluate it. I'll ask you some questions. Is this a good idea or a good design? No. Some people are shaking their heads. Some people are already bored with the single cycle microarchitecture. They're saying, let's move on. And I understand that, but everybody needs to understand the single cycle microarchitecture to do the lab. That's important. Why no?
Because the clock speed is determined by the log list instruction.
That's right, yes.
All the instructions that were taken are directly
That's right, yeah. Some instructions may be processed much faster than the longest instruction, right? That's what you're saying. Yes?
I'd argue that it's a good design given this architecture because the longest instruction would just be taking one cycle. And like you can read from memory, or I guess you can store it in memory throw one, which is probably your slowest path in a single cycle. So you can do everything in a single cycle, so that's what we'll do.
Well, yes, you could do everything in a single cycle, but there are 2 components, as we will see, to the performance of a machine. How many cycles it takes to process an instruction, and how long that cycle is. So with this design, you're making the first component 1, but you're making the second component, how long that cycle time is, very long. There's lots of hands. Yes, you have.
Also, if you're thinking of it from a more realistic standpoint, when you start adding in a lot of stuff to the computers, how like virtual memory and that sort of thing, it's kind kind of hard to make everything single cycle because including virtual memory, you have page faults, you can have a bunch of different things that can go wrong and that can delay it.
That's right, yes. So some things naturally should take very, very long, right? What if you need to access this, for example, in an instruction? Then this becomes a little bit contrived, if you will, as I will show you in the next slide. Yes?
Also, if you like allow if you set the clock rate to that longest cycle, to the longest instruction, that might really not be as often executed. So you're really slowing down your common case. Because
Exactly.
case must be really simple.
Exactly. So we will, okay, let me continue. We will get to a lot of these good things that you all pointed out. So when is this a good design? This is a good design if all instructions take the same amount of time and if they take short, perhaps, right? When is this a bad design? Well, we've already given some arguments as to when this is a bad design. And how can we design a better microarchitecture? And I'll ask you these questions at the end of the microcoded machines also, so you might as well be prepared. So let's take a look at, let's analyze this. I mean, it's clear that every instruction takes one cycle to execute here, which means that cycles per instruction is strictly one. This is a common metric that's used to evaluate microarchitectures. The problem is how long each instruction takes is determined by how long the slowest instruction takes to execute. Even though an instruction may not need that long to execute. And clock cycle time of the microarchitecture is determined by how long it takes to complete the slowest instruction, which means that's the critical path of the design, right? So let's go back to the basics. We looked at 6 phases of the instruction processing cycle to what each instruction should complete. Do each of the above phases take the same time for all instructions? No, right? For some instructions, you skip some of these steps. Not all instructions access their operands from memory, for example. Load does that, but ALU operations don't do that. So let's analyze. Let's still be simple, but look at some of these instructions that we look at. Let's assume that the memory units are 200 picoseconds, ALU and adders are 100 picoseconds, register file is 50 picoseconds, and other combination logic is 0 picoseconds. If you look at R-type instructions, they need to, well, all instructions need to be fetched and decoded. I guess jump doesn't necessarily need to be decoded, or decode takes, well, they don't need to access the register file, because I assume the other combination logic is 0 picoseconds, just to make life easier. Obviously, this is not the case, right? This is just a simplification, just to show you different instructions take very, very different number of cycles, or different amount of nanoseconds or picoseconds, if you will, different latency. So if you look at this, jump takes 200 picoseconds, whereas a load word, which needs to go through all of these steps, needs to be fetched, decoded, access the register file, access the ALU to compute its address, access memory to do the load, and write back to the register file. So you need 600 picoseconds. So even with our magic memory and register file assumptions, there is a big discrepancy in terms of the processing of instructions. This instruction really can complete in 1/3 of the time you can execute the load word. Right? So there's no reason for you to make your cycle time as long as you execute load word. But with a single cycle microarchitecture, you're stuck. Well, I'm not going to go through this in detail, but this is just to show you that these numbers actually match. So I'll let you do this analysis based on what I've shown you. These are slides for your benefit to figure out the critical path for different instructions. But if you look at the critical path for load, for example, there could be 2 possible places for a critical path because you're updating the program counter, PC+4, which takes 200 picoseconds. We assume that the combination logic delay is 0. This adder, oh, actually it's 100 picoseconds, sorry. You just need to add. And there is some combination logic there. But this is the critical path that the load needs to take. Fetch, decode, access the register file, do something in the ALU, access memory, write back into the register file. That's how you get the 600 picoseconds. Store word, branch taken, and jump. You can look at this. How about control logic? This calculation was done without anything related to control logic, right? Control logic doesn't affect the critical path. It could, right? Yes?
The more complicated, the more check you have to do, the more complicated your control logic has to be to
Exactly, yeah. It could. I've ignored this in my analysis. But when you're actually analyzing the critical path, you should take into account the control logic as well. So there are usually three things, actually, that could affect the critical path significantly. And those are, I guess, the time it takes. I guess I can do this. Time it takes to access memory. And you've seen that load is the critical path because it's doing an access to the memory. To go through the ALU is to do an ALU operation. And the third thing is to determine the control signals. This could be your critical path. If it takes too long to determine the control signals. In fact, if your instructions are complex, this third one could be your critical path. And actually, this was a machine that's a very early machine in the 1960s or late 1950s, maybe even. This was a corporation, Canadian corporation, Control Data Corporation, that was competing with IBM. And they actually designed one of the first out-of-order execution computers in the world before IBM did. This was the precursor to that design, CDC 5600. And they had a control store whose access took too long. Now, they didn't have a single cycle design. They were more realistic than what we had. So what they did was they accessed the control store and they got the control signals for the next 2 cycles. Because it took too long to access the control store, they just got the control signals for the next 2 cycles so that they could amortize the cost of access. So there are machines where control can actually be on the critical path. Yes?
Is that what MIPS does?
Which MIPS does?
The one you talked about.
Well, a particular implementation of MIPS. I don't know how R4000 does the control logic.
I mean, I'm wondering if that's the reason for the branch delay slot.
Oh, no. I will tell you what the reason for branch delay slot is. That's not the reason, though. Okay, what is the slowest instruction to process? Well, memory is really not magic, right? Given you a single cycle memory. What if memory is sometimes 100 milliseconds to access? This is what really kills your single cycle design. And what if memory sometimes takes 50 milliseconds, sometimes takes 100 milliseconds? Now you have variable latency. How do you account for that? Well, if this is the case, does it make sense to have a simple register add or jump to take 100 milliseconds plus all else to do a memory operation? Obviously not. And what if you need to access memory more than once to process an instruction? I guess I'll ask you the question, which instructions need this? What instructions access memory more than once? Load. How many times does it access memory? That's right, yes. You need to fetch, and then you need to get to your data from memory, read your operand that you're going to store in the destination. Actually, all instructions need to access memory, right? They need to be fetched. If you have a cache, and you hit it in the cache, you're lucky, but that's what our magic memory abstraction is. You always sit in your cache in one cycle. What about back's index instruction? You need to do a 3-dimensional array access. So you access memory many, many times in that case, right? Or you provide multiple ports to memory, right? Then your design becomes more expensive. So what are the downsides of single-cycle microarchitecture? It's really the complexity. It's contrived, it's hard to implement, All instructions are as slow as the slowest instruction. It's inefficient because of the same reason. But you also need, it's not necessarily efficient in terms of hardware cost, right? You really need to provide the worst case combinational resource in parallel as required by any instruction. So if you have a wax index instruction or repeat MOS, how do you do that? Do you provide many ports of memory? Or do you lengthen your clock cycle so much that it becomes ridiculous? And I've already told you that, right? If a resource is needed more than once by an instruction during different parts of the instruction processing cycle, you need to replicate that resource. Like an ALU, like an adder, we replicate PC+4. You cannot use that ALU for program counter computation. So this is really not necessarily the simplest way to implement an ISA, especially a complex ISA. It's also not easy to optimize and improve performance, right? Optimizing the common case, you wrote up the common case. That doesn't work, right? What if all your instructions are added except once in a blue moon you do a memory access? But your cycle time is now determined by your memory access, right? Like memory access, I mean load. Every instruction does a memory access, right? An instruction that does multiple memory access. You cannot do that in a single cycle microarchitecture because you're bound by the worst case execution time. So there are several design principles that this microarchitecture actually violates. And this is important to know. I summarize these as critical path design, bread and butter or common case design, as one of you brought up, and balanced design. What is critical path design? You find the maximum combinational logic delay and decrease it. Minimize the critical path, maximize the clock cycle time. I guess you could do it here in this case, right? You could try to minimize your critical path, except your critical path is still dominated by the worst case, not the common case. This is the common case design says that spend time and resources on where it matters, really. So improve what the machine is really designed to do, what the machine is really going to execute. Don't optimize for the uncommon case. If your machine is doing ads most of the time, optimize the ad. Does that make sense? Common case should be fast. Uncommon case can be slow. Of course, again, there's a trade-off here, right? If uncommon case happens once a day, and if it takes to process that for a week, then you have a problem. You still need to optimize it such that that doesn't become the bottleneck. But you don't need to optimize it as much as the common case. So this is violated by the single cycle design. Balanced design, basically you balance instruction and data flow through hardware components. Balance the hardware designed to accomplish the work. This will become, basically the resources you need here are not really balanced, right? They're determined by the worst case execution of the longest instruction. You need to provide the resources in a single cycle for that to happen, especially if you want to optimize the design, right? Minimize the critical path. So single cycle microarchitecture doesn't do well in this principle also. So one other example of a balanced design is if you're designing a machine that can execute multiple instructions. Let's say you want to finish 5 instructions per cycle. We haven't covered superscalar execution yet, but think about that. If your fetch engine can fetch only 1 instruction per cycle, can you actually finish 5 instructions per cycle? The answer is no, right? Maybe once in a while, if you accumulate instructions, you could, but not in the steady state. And people have actually made these mistakes in design before. So you really need to provide resources such that the design is balanced across different components. Another balanced design, I guess, you need to provide the memory bandwidth that's necessary to be able to fetch the data operands you need, right? If your memory becomes a bottleneck, then your design may not be balanced. Okay, so maybe we should take a 5-minute break before we start with multi-cycle microarchitectures. So the goal in multi-cycle microarchitectures is to let each instruction take only as much time as it really needs. And I say close to because you'll have a clock cycle. It's going to be very hard to optimize exactly the number of picoseconds that you need. So the idea is determine the clock cycle time independently of instruction processing time. We tied these two things together before, now we're going to untie them. Each instruction takes as many cycles as it needs to take, which means that there are multiple state transitions per instruction, and the states followed by each instruction is different. And I've already gone through this and shown you that we're going to pick choice 2 now, take multiple clock cycles to transform the state at the beginning of the instruction to state at the end of the instruction to implement the ISA specification. Which is essentially this. Basically, we're going to chop it up, chop instruction processing into steps. Step 1, process part of the instruction in one clock cycle. Step 2, process some other part of the instruction in the next cycle. Then you have ... and at the end, you generate the architectural state at the end of the clock cycle, and you go to the next instruction. Right? So benefits, now you can keep reducing the critical path regardless of the worst case processing time of any instruction. Right? You've decoupled your clock cycle time from the worst case processing time of the longest instruction. You can now optimize the number of states it takes to execute important instructions, right, that take up much of the execution time. You're not bound by the worst case again. So this is good for common case design. If your machine is executing adds most of the time, you minimize the number of states, number of cycles it takes to execute add. And you also minimize the critical path for your ALU, which will actually improve the performance right now. Whereas before, it wouldn't improve performance significantly because your cycle time is dominated by some other thing. And this is also a balanced design because you really don't need to provide more capability or resources than really needed in a single clock cycle because you've chopped up the work. So an instruction that needs resource X multiple times does not require multiple X's to be implemented unless those X's need to be used in the same clock cycle. Before it was, you needed to replicate that resource if that resource was used during the processing of the entire instruction. Right? Now you need to replicate only those things that you want to be used multiple times in the same clock cycle. And the clock cycle is much smaller than the time it takes to do an instruction. So this leads to more efficient hardware because now you can reuse hardware components multiple times for an instruction. And we will see this. So let's briefly give you a performance analysis. Execution time of an instruction is really this. The number of cycles it takes to process an instruction and the clock cycle time. And you can now optimize these independently. Execution time of a program is the sum of this over all of the instructions that you need to execute. Right? That's how long your program takes. And you could also specify this. This is, some people call this the iron law of performance in computer architecture. Execution time is equal to the number of instructions, average cycles it takes to execute an instruction, times the clock cycle time. And you could improve the execution time by, I guess, reducing any of these. Right? You could reduce the execution time by reducing any of these. Single cycle microarchitecture performance, your CPI is always 1, clock cycle time is long. Multi-cycle microarchitecture performance, CPI is different for each instruction, and average CPI is hopefully small, average cycles per instruction. And clock cycle time, make it short as you want. Now you have 2 degrees of freedom to optimize independently, right? These 2 things. You can optimize independently, right? Okay. So this is just an aside for you to think of CPI versus clock cycle time. These are usually at odds with each other. In fact, reducing one increases the other for a single instruction. Right? Because you need to go through more steps now, more states to finish the instruction if you reduce the clock cycle time. Well, I've already given you the reason, I guess, right, why. But think about it. For a single instruction, these are actually, I don't want to say maybe almost always, but I'll say usually at odds with each other. If you find a case where these are not at odds with each other for a single instruction, let me know. But you can amortize the average cycle per instruction by concurrently processing multiple instructions. Keep this in mind, that's why this is an aside. A multi-cycle microarchitecture that we will discuss will not do this, but you could devote the same cycle to do multiple instructions at a time. And that's what pipelining and superscalar execution do. And that way, they can amortize the average CPI. What do they do? Well, in the same cycle, they process multiple instructions. So cycles per instruction goes down because you're having multiple instructions, right? You're doing multiple instructions per cycle. Okay. So this is very fundamental, though. For a single instruction, for the processing of a single instruction, if you're reducing the clock cycle time, that means you're having more cycles to execute it. Okay, let's take a look at the multi-cycle microarchitecture, one implementation of it. And we're going to look at the microcode implementation. How do we implement it? This has been around for a long time, as you can see in your optional reading. How do we realize these microcoded machines? Basically, one can implement this process instruction step, if you will, as a finite state machine that sequences between multiple states and eventually returns back to the fetch instruction state. And you can completely specify the state machine for an ISA. A state, what is a state? It's defined by the control signals asserted in it. Oh, I don't know how that happened. But I pressed another button. And in the current state, you determine the control signals for the next state. So this is what we're going to do, basically. We're going to chop this up into different states, and each instruction will have different states. So a basic architecture, a basic multi-cycle microarchitecture, instruction processing cycle is divided into states. So this will be divided into states for each instruction, and it'll obviously be different for each instruction. And a stage in the instruction processing cycle actually can take multiple states. So fetch, for example, it could take multiple states. And we will see that it will. We will sequence from state to state to process an instruction. And the behavior of a state will be completely determined by the control signals. And the behavior of the entire processor will be specified by a finite state machine. So in a state or a clock cycle, control signals will do two things. How the data path should process the data in that particular clock cycle, and how should we generate the control signals for the next clock cycle. Make sense? I'll give you some terminology to clarify some things. Well, you already read this in Appendix C, hopefully. But control signals associated with the current state are called a micro-instruction. These are, when I say micro-instruction, these are the control signals associated with the current state. Now, act of transitioning from one state to another is really determining the next state and the micro-instruction for the next state. Right? This is called micro-sequencing. We're really sequencing from state to state. Right? Control store, I've already shown you this. This stores control signals for every possible state in the machine. Basically, this is the store for micro-instructions for the entire finite state machine. Remember, each state is specified by a micro-instruction, control signals, and control store stores for each state the micro-instruction. And as long as you have in this control store all possible micro-instructions that you could possibly encounter for any state, that's your machine. Right? And a micro-sequencer determines which control store location you're going to access. It determines which set of control signals will be used in the next clock cycle, in the next state. So you have a micro-sequencer that tells you, access, my next state is going to be this. So get me the control signals associated with that next state and feed them into the data path. Okay, so what happens in a clock cycle? Before we get into the design, let's take a look at that. I've already told you two things happen. The control signals, or the micro-instruction for the current state, determine two things. what happens in the data path, the processing in the data path, and the generation of the micro-instruction for the next cycle. I'll give you the supplemental figure 1. And data path and microsequencer operate concurrently. Remember, microsequencer determines what is your micro-instruction, what is your next state. What should your address be in this control store? Actually, let me go to this. Well, this is my drawing. I don't know if you can see this, but basically, this is a clock cycle, right? Two things happen. This is important. Processing in data path for cycle n, for this cycle, and generation of control signals for cycle n plus 1. And at the end of this clock cycle, the results of this processing are latched into the latches, and the control signals for the next clock cycle are latched into the latches. Well, this is a good clock cycle, if you will. Here's a bad clock cycle for you. In this long clock cycle, you generate the control signals for cycle n, for the current cycle, and you also do processing in the data path for cycle n. This is a bad clock cycle because step 1 is really dependent on step 0, right? The data path operations are dependent on the control signals that you need to generate. And if you're generating your control signals in the same clock cycle as the operations that you're doing, then that's bad. If step 0 takes non-zero time, and it does, believe me, we will see that, clock cycle increases unnecessarily. That's why you're much better off if you determine your clock control signals in the previous clock cycle. Make sense? So this violates the critical path design principle. That's why this is a good clock cycle. You determine your control signals for the next cycle in the previous cycle. Okay? So I answered that question with my hand-drawn figures, since my PowerPoint art is terrible. Okay. So I've already given you what's happened. So and you've seen this. This is figure C1 from Appendix C. And we will look at LC3B in this case because it's a lot simpler. So you have control that's happening in the same cycle as the operations that are taking place in the data path. And these are tightly coupled. Right? Control gives you the control signals that you will use. And 26 of them, they're all specified in your handout that you have. Actually, if you look at your handout, you can see this. This is the first figure. 26 signals determine what processing goes on in the data path and memory. And memory is really part of the data path. And I/O is also really part of your data path. And some of your control signals are used to determine, in conjunction with what happens in the data path, what your next set of control signals will be. So these 35 control signals completely specify your state. Okay. So what determines the next state control signals? Let's discuss that first. This is discussed in Appendix C. So if you read it, this will all be reviewed, hopefully. Obviously, what's happening in the current clock cycle, right? And what's happening in the current clock cycle is kind of summarized by some of these things. Is the memory ready, for example? Remember, memory is not magic anymore. We're beyond the magic stage. Memory can take milliseconds if it wants. Well, if it has to. So memory will give us a signal saying it's not ready with the data. It's done the action that you asked it to do. But it may not be ready in any given clock cycle, right? And we will see this. So what's happening in the current clock cycle determines what your next state could be. The instruction that's being executed also determines what your next state could be. Whether the condition of a branch is met, if the instruction being processed as a branch, determines what is your next state, right? Because if your instruction, your target is different, your next instruction is different. Whether the memory operation is completing the current cycle. Okay. Also, there are other control signals here that determine what should your next control signals will be, and we will cover this. These are used by the microsequencer to figure out, well, let me actually remove this opcode function. We don't have an opcode function anymore, but we have an address into the control store, and a microsequencer computes the address into the control store to get the next state's control signals. And these are determined by some of these bits that we will cover. Okay? Okay, I'll let you read the section. Okay, so let's take a look at the state machine that specifies behavior of LC3B completely. And you guys hopefully have studied LC3B. Let me actually pull out these appendices just in case I need them, because I don't know the ISA fully, obviously. That's why the manuals are there. Well, I know some things about the ISA, but I don't know exactly everything. How did we come here? Okay. The behavior of the microarchitecture is completely determined by the 35 control signals and the additional 7 bits that go into the control logic from the data path. What are those 7 bits? These are the 7 bits. So these are your 35 control signals in the current cycle. They're fed to the data path, they're fed to the microsequencer, and also you get some bits output from your data path that determine what your next state should be. And your behavior is completely determined by that. And these 35 control signals completely describe the state of the control structure. Now, we can completely describe the behavior of the LC3B, this ISA. We can completely implement it as a finite state machine. And you know what a state machine is, right? You have a directory graph of nodes and arcs. A node corresponds to the state, and arcs show the flow of which state you go to from the current state. Let's take a look at this state machine. Well, obviously you need to specify uniquely each state, right? You guys remember 240. Each state is uniquely specified by means of state variables. Or you can think of this as the address of the state. Or address into the control store that specifies uniquely the control signals. In this LC3B state machine, we can move to it. This is the second figure in your handout. Oops. I don't know how we're jumping around, but we have 31 states, and each state is labeled with its address or the state variable that specify it. Then we encoded it with 6 state variables, and your handout describes why 6 states to provide extensibility. You really need only 5 state variables, right, to encode 31 distinct states. Okay, let's look at the state machine. Can you guys see this from the back? Yes, somewhat, sort of. Is it better to use the dot camera? I guess, can we use both? Is that possible?
Yes.
Yes. That's a confident yes. I guess if we use right projector, we can use both, right?
Yes.
Okay. Otherwise, there is a resource conflict here. But then I cannot use the third thing. Well, I've been writing to the bottom of the screen anyway. So let's do the dot camera. Well, this is still warming up. Okay, while we're warming up. So, examples. States 18 and 19 correspond to the beginning of the instruction processing cycle. This is the beginning of the instruction processing cycle. And this state specifies what goes on in the data path in it. And these 3 states collectively, states 18, 19, they're the same state really. And there's a reason why they're the same state, and I'll get back to this later, or you'll figure it out before I get back to it. This is the beginning of the fetch phase. The next state and the next state. At the end of these 3 states, the instruction is fetched. Instruction specified by the program counter is fetched into the instruction register. And program counter is incremented by 2 because instructions are 2 bytes long in LC3B. Is this better? You tell me. I guess I could zoom in. Okay, so let's focus on these three states. Okay. Well, let me actually move on. I'll ask you these questions later on. Let's take a look at the data path design. And we'll look at a single bus data path design. Obviously, your state machine is dependent on your data path, what goes on in your data path. And we'll have a single bus data path design. We'll cover these advantages and disadvantages in a little bit. Maybe I should put the data path design here instead of the state machine. So let's swap these two things. Okay. You should be looking at your handouts if you cannot see the screen very well. Okay. Well, I don't know if this is a good idea. Let's zoom out. Okay. So this is a data path design for the LC3D. I guess I'll zoom up even more, so that you can see almost the entire data path. This is a single bus design. You have a single bus that connects many of the components. And we'll get back to this. So state machine specifies what should the data path do in each state. In this case, this state, these three states are part of the fetch of an instruction. And we've broken it into three things. The first state. What is happening in the first state? The state machine says, take the program counter, put it into the memory address register. And also, increment the program counter by 2. So let's take a look at how we can accomplish this with the appropriate control signals in the data path. Let me orient you to the data path. Can people see this from the back? Yes?
It's small.
It's a bit small. Well, you could look at your handout. This is in your handout. This is the third page. I don't know how I will be able to show you exactly how this is done. But let me orient you to the data path. This is very similar to the MIPS data path we've looked at, except it does implement things in a different way because it's a single bus design. But, okay, here's the memory. And memory is not magic anymore. We have a memory address register. We can load the memory address register, and we can enable the memory to read or write. If we do that, then the memory outputs data into the memory data register. Well, it comes from here. And it's a little bit complicated here, which we will get into. But we can ignore some of the complications for now. But memory takes as input the memory address register, write enable bits, and memory enable. And outputs the memory data that goes into the memory data register. And memory can now take multiple cycles. And when the memory actually outputs data into the memory data register, it asserts this ready bit. So there's a ready bit associated with memory now. So in the first cycle of processing of any instruction, what we need to do is take the program counter, place it into the memory address register. That takes one cycle, right? We latch the program counter into the memory address register. So program counter sits here. Basically, we need to provide a path. The data path is already provided. So the program counter needs to be gated onto the single bus, which means that this gate PC signal should be asserted. And program counter, in that case, flows through the single bus and hits the memory address register. And if we assert the signal ld.mar, load memory address register, then the program counter can be latched into a memory address register in the first cycle. Right? So in the micro instruction associated with the first state, here, gate PC should be set to 1, load MAR should be set to 1. Right? And all the other things in the data path that are driving the single bus should not be driving the bus. Does that make sense? So you guys know the difference, you guys know the idea of gating, right? you could gate a value onto the bus. And there could be multiple things that could possibly load or gate onto the bus. But you really want only one thing to load the bus, right? The program counter is a 16-bit value, and the bus is 16 bits. You want to set the gate PC signals to 1, and every other thing that could be loaded onto the bus should not be loaded, which means gate ALU should be 0, gate shift, there's a shifter here, should be 0, and gate MAR-MUX. This is the MUX that picks whether the memory addresses should be gated as computed by a load or store instruction onto the bus. So only this gate signal should be asserted. Okay? So that's how you implement the first state. Well, there's some other thing that's going on in the first state, right? The program counter is incremented by 2. So if you look here, your data path has some logic that increments the program counter by 2, an adder. And your program counter can come from multiple places. Ignore some of these other places for now. This is very similar to the design we looked at because your program counter is not always implemented sequentially, right? Incremented sequentially. Sometimes you take the jump target, for example, from an adder that's here, as specified by the jump instruction. But in this case, in this state, we're not going to take the jump target because we're incrementing the program counter by 2. So we're basically going to set this PC MUX control signal to select PC plus 2, and we're going to enable the load of the program counter. Does that make sense? So in the micro instruction, the control signals that select this MUX signal should select this input, and load PC should be asserted in the micro instruction. Now we have specified the state, except all other register enables should be deasserted in the micro instruction, right? Because this state doesn't specify any other register to be loaded. So, for example, your load register signal should be deasserted because we're not loading the register file in this state. Make sense? So that's the first step of the fetch. Now we've loaded the address into the memory address register. In the next step, we move to the next state. The microsequencer tells us we're done with this, so the next state is unconditionally this state. Right? So how does the microsequencer do this? Well, I guess that's why I have these figures for you. Let me figure out the microsequencer. If you read this, microsequencer. Oh, no, that doesn't work that way. Yeah. Is a structure like this. It gives us the address of the next state, and address of the next state is now unconditionally determined by these J bits that are stored in the micro instruction. The micro instruction also stores some J bits that tell you the address of the next state. And these J bits are set to, what is that, 33? Yeah, 33. And these signals, condition signals, are asserted such that you take the output of these, these are essentially zeros, right? Such that J bits determine unconditionally the next state. Does that make sense? So in this state, you also have some bits in the micro instruction that tell you J bits, which are the bits for the address of the next state, should be 33. So you jump to the next state unconditionally because you set these J bits to 33. Make sense? Okay. This will become more clear soon. So let's finish the instruction fetch cycle before we part. So we've loaded the memory memory address register, and we've jumped to the next state. Now in the next state, we need to access memory to get the instruction, right? The address is already in MAR, so we need to assert the control signals of the memory such that memory is enabled. This is similar to the memory read signal we had in MIPS. So this signal is asserted, and write enable signals for the memory are deasserted. They're not enabled in this case. And memory will take its time to access data, and memory will not be ready in one cycle. Let's assume memory takes multiple cycles. Now we have variable latency in memory. So until memory becomes ready, we stay in this state. So if memory is not ready, the next state is still 33. And now memory can take 1,000 clock cycles if it wants. Until the memory asserts this ready bit, we're going to stay in this state waiting for memory. Yes?
So we can't do anything until memory is ready.
That's right. Yes. You cannot do anything until the memory is ready. But we will fix that problem later on. Make sense? So at some point, memory becomes ready and it asserts this ready signal. And this, if memory is ready, if you look at the state diagram, your next state is not 33, but your next state is 35. So let's go back to the microsequencer. So your microsequencer has some J bits. Now you have a conditional state transition, right? In this state, you either go to 33, your J bits are 33, or next state is 35. So your address of the next state is 35. So how do you do that? This is a state where you're actually accessing memory. So we set these condition bits such that one of the bits in the address of the next state can be affected by the ready signal coming from memory. So the condition bits are set to, I guess in this case, 1 and 0, or 0 and 1, such that the ready bits can take effect. And if ready bit is 0, let's say we set these to 33, and you can figure out the encoding of 33, right? What is it? 1, 0, 0, 0, 0, 1. That's the address of the next state, if memory is not ready. But if memory becomes ready, then the address of the next state will be 1, 0, 0, 1, 1. Right? That's 35. And that's enabled by setting the J bits in the micro instruction to 33, setting the condition to associate with this state to, I guess, this one to 1 and this one to 0, and setting this IRD bit to select this output in the microsequencer. So once the memory becomes ready, we jump to state 35. And what does state 35 do? Before we part, let's look at that also. What state 35 does is, remember, we're fetching the instruction. When the memory is ready, it outputs its data into MDR. State 35 simply needs to take that data and memory data register and place it into the instruction register. So ignore this logic for a while. You take the data from the memory data register and gate memory data register onto the single bus, because now the bus needs to take memory data register and place it into the instruction register. So the control signals you need to enable, ignoring these, are gate MDR should be asserted, all of the other gating signals should be deasserted, and load this instruction register. Load instruction register should also be asserted so that you can specify the state. And then you unconditionally transfer to state 32, which means that your J bits should be 32 and your condition bits should be 0, such that nothing is affected in your microsequencer. And this is the decode state. Now we're going to decode the instruction. But we can do that when we come back on Wednesday. So we'll completely cover this microprogrammed architecture. Please read Appendix C and Appendix A so you will be able to follow the plot more easily.